Okay guys, so in this video, I am just going to go through all of your examples for this unit. All of the other notes are going to be found in the slides. I recommend that you actually go through and read the slides. So here we go. Let's identify our number of significant figures in the following problems. So remember, anything that's not a 0 is automatically significant. So this 4 we know is significant. These 5, 4, 3, and 2 are significant. Zeros between two significant digits are also significant, but these trailing zeros are not. So we have 1, 2, 3, 4, 5, 6 significant figures. So 6, and I'm just going to write S, Fs. There we go. All right. Again, non-zeros are always significant. 0 between two non-zeros is significant. And then because we have this decimal point here, this 0 is also significant. So I have 1, 2, 3, 4, 5. All right, significant, significant, because they're both non-zeros, and then zeros between them are significant. Think of it as like your non-zero numbers are giving your zeros a hug, which makes them significant. That's just one way to look at it. So I have 5 significant figures again. And then non-zeros, always significant. This 0, because it's after a decimal place with a non-zero in front of it, is also significant. The zeros in front of that are not, because there's not a non-zero number. Now, if I were to put a 1 or something right here in front, then all of these zeros would be significant. Or if this was a 1 right here, then they'd all be significant. If I stuck in a real digit anywhere in between these, that would make them significant. But because there's not, it's just 4. All right, so let's go to our next one. So let's do our next 4 examples. So again, non-zero is always significant. There's no real number in front of this decimal place, so the 0 is not significant. So I have 4. Significant, significant, and they're hugging all these non-zeros, so they are significant. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9. This 5 is significant. These 2 zeros are not. So 1. And then I have 5 period or 5 dot here. This dot makes these zeros significant, and that 5 is also, which is why I included this example. So in problems you'll see in the future when we're doing calculations, you might see something like 500 dot grams of blah, blah, blah reacted. The reason why it's 500 dot is so that you're going to have 3 significant figures in your answer. Again, I get that significant figures are a little bit difficult, but the more you practice with it, the easier it is, and the more you're going to get it. It's just one of those things that you have to practice doing over and over again. All right, so let's do addition subtraction. In addition subtraction problems, we're looking for the least number of decimal places when we do the problem. So I have 2 decimal places in this one. I have 1 decimal place here. So I'm going to round my final answer to 1 decimal. Oh my goodness, what is happening with my pen? Oh, goodness. Let me try again. So I'm rounding to 1 decimal place. So I'm going to do the whole problem on normal. Throwing things. So 12.06 plus 10.1. My unrounded answer is 22.16. I'm rounding to 1 decimal place. So looking at this 1 here, that's a 6. 5 or above, give it a shove. 4 below, let it go. So we're going to round that to 22.2 is my final answer. On this one, I have 4 decimal places, 2 decimal places, so I'm rounding to 2 decimals. That's what 2 decs is going to mean. 2 decimal places. So 1.0089 minus 0.02 gives me this number as my unrounded answer. And I'm rounding to 2 decimal places, so I'm looking here. Again, this is an 8, so I'm rounding up, and it's going to become 0.99. You can also put 0.99. It's the same thing. This 0 does not affect anything, so we just need 2 decimal places. All right, last one, I have 0 decimal places and 2 decimal places, so I'm going to want 0 decimal places in the final answer. So 234,908 minus 11.22. Unrounded, I get the answer of 234,896.78. I went 0 decimal places, so I'm looking at this number here. So we're going to round it to 234,897. So there you go. Those are your addition subtraction problems. And multiplication division, you're just looking for the least number of significant figures total. So I have 3 significant figures in this number. I have 4 in this one, so I want 3 in my final answer. I'm going to round to 3. So 67.3 times 234.0 gives me this number unrounded. Oh goodness, that 2 did not look right. Aha. All right, so I have 3 significant figures. So these first 3 numbers, that's a 4. So we're just going to turn that into 15700. Okay. So we only want 3 significant figures, so we're just going to add 2 zeros there. All right, next one, we have 14.22 divided by 8.0. I have 4 significant figures here, 2 here, so I want 2 in my answer. So unrounded, I get 1.7775. I want 2 significant figures, so that's a 7, so that's going to become 1.8. All right, last one, I have 2 significant figures, 3 significant figures, so I want 2 significant figures in my answer. So 0.0022 times 14.1 becomes 0.0308. I want 2 significant figures in my answer. So these numbers are not significant, so we're starting here actually when we're looking at number of significant figures. So we're going to end up with 0.031. You could also write 0.031 because these 2 are not significant here. So again, when you multiply, divide, or add and subtract, significant figures are just telling you how to round your final answer. So now let's talk about dimensional analysis. So when we do dimensional analysis problems, it's a way to set up problems where we use conversion factors. And I know that you're going to want to go, but I can just divide or multiply by these conversion factors. Why do I have to set them up like this? And the reason we do this is because we'll do more advanced chemistry calculation conversions later where it's very many multi-step. And having it set up this way, it allows you to cancel your units so you know you're setting things up correctly. So please just do it this way. I know it's going to feel dumb at first, but it's really going to help you in the end. So wanted is your desired unit you're solving for. Given is the unit you start with, and that's what you're going to base your significant figures on in your answer. Data will be your conversion factors, and find is where we're going to show our work. So we're going to do, I think, 4 examples of this. It's 3 or 4. So wanted, given, data, find. And I'm going to go ahead and write that out for you. So wanted, we are solving for how many grams, so wanted is grams, are in 234 kilograms. So given is 234 kilograms. Data is going to be my conversion from grams to kilograms. So there are 1,000 grams in 1 kilogram. So I'm going to set it up where it's given on top and then data wanted on top, data given on bottom. And I'm going to set it up actually in a bracket form instead of this fraction form. It's the same exact thing. I just like the way this looks better. So given goes in my first bracket, so 234 kilograms. And then I have kilograms on top, so kilograms is going to go on bottom, and I'm going to use my data there, so 1 kilogram. My desired or wanted units go on top, so that's 1,000 grams. And when I do it this way, I'm able to cancel out my kilograms and kilograms, and I multiply everything on top together and divide by everything on bottom. So 234 times 1,000 divided by 1. And the best part about doing these metric conversions is that you don't have to worry about significant figures because they don't change. So 234 times 1,000, 234,000 is your final answer. Grams, make sure you include your units. right, let's do the next one. It says if 2.54 centimeters are in 1 inch, how many centimeters are in 3 feet? So wanted, we are solving for centimeters. We are given 3 feet. And then our data, we're given one data point, which tells us 2.54 centimeters is 1 inch. We also know inches to feet because we have to go centimeters to inches to feet. So then we need to know that 12 inches is in 1 foot. So we're going to do our little find over here. So we are given 3 feet. Feet on top, so feet are going to go on bottom. 1 foot is 12 inches. Inches on top, so inches are going to go on bottom. 1 inch is 2.54 centimeters. So then feet cancel, inches cancel, inches cancel. So 3 times 12 times 2.54 divided by 1 times 1. So 3 times 12 times 2.54. So my unrounded answer is 91.44 centimeters. Okay, and we're going to look at our given to see how many significant figures we need. We just need 1. So this is going to become 90 centimeters. What's your final answer? All right, this one says, how many decimeters are in 28.9 meters? So we want decimeters. We're given 28. Oh, I hit a button. 0.9 meters. And our data is that for every 10 decimeters, we have 1 meter. So we're going to find. So 28.9 meters. Whoa. Meters on top, so meters on bottom. 1 meter is 10 decimeters. Meter cancel, meter cancel. 28.9 times 10 divided by 1 is 289 decimeters. And again, because it's a metric conversion, we don't really have to worry about our significant figures because that's 3, and that's still 3 again. I do believe we have one more. Oh, I hit right there. Oh, goodness. Okay. How many minutes are in 9 weeks? So this one's going to be more of a much bigger problem. So wanted are minutes. We are given 9 weeks. So we need to know minutes to days to weeks. So there are 60 minutes. Oh, minutes to hours to days to weeks in 1 hour. 24 hours in 1 day. And then there are 7 days in 1 week. Hopefully I can squeeze this whole problem in. I'm going to switch colors just in case it's harder to squeeze it in so you can tell the difference at least. All right, so I have 9 weeks. Weeks are on top, so I'm going to put weeks on bottom. So in 1 week, I have 7 days. I guess I could just write day. One day is 24 hours. And 1 hour is 60 minutes. So see how, because I set it up this way using dimensional analysis, I'm going to be able to cancel my units, and I can keep track a lot easier than just multiplying all these numbers together. So weeks cancel, days cancel, hours, and I'm left with minutes, which is what I wanted. So 9 times 7 times 24 times 60 times 7 times 24 times 60. So I get this big old number here. So 90720 minutes. And I want one significant figure in my answer. So it's going to become 90,000 minutes. That was supposed to be an underline. It looks like I crossed it out. 90,000 minutes. All right, so let's talk about our next thing, which I do believe is scientific notation. All right, scientific notation is standard notation. So when you do scientific notation, what we're looking at is the exponent. If your exponent is positive, it's going to be a big number or a number bigger than 10. If your exponent is negative, it's going to be a little number or a number less than 1. And if your exponent is 0, you're going to move your decimal place 0 times. So it'll be a number between 1 and 10. So if we look at this, we have a positive 4. So positive equals a big number. So I'm going to move my decimal place 4 times to make this number big. So I'm going to move it 4 times in this direction. So 9.003, and move it 1, 2, 3, 4. So this becomes this number. Okay. On this one, I have a negative exponent, so it's going to be a small number or a little number. So I'm going to move my exponent 4 times in this direction to make it small. So 7.02, we're going to go 1, 2, 3, 4. And you can also put that 0 in front if you wanted to. All right, and this one where it's 0, I'm moving my exponent 0 times. So 3.0 becomes 3.0. So now let's talk about the reverse of that. So in the reverse of that, I have the standard form, and I'm going to write them in scientific notation. So I have a little number, so I'm going to have a negative exponent. So I'm going to move my decimal place to make this only have one number in front of the decimal point. So I'm going to move it to right here. So I'm going to move it 1, 2, 3, 4, 5 times. This becomes 8.7 times 10 to the negative 5. All right, on this one, I have a big number, so I'm going to have a positive exponent. So my decimal point's there. I only want one number in front of the decimal, so I'm going to move it to right here. Move it 1, 2, 3, 4, 5, 6, 7 times. So 7.12 times 10 to the 7. And on this one, I already have just one number in front of the decimal, so I don't need to move my exponent any time. So it becomes 1.2 times 10 to the 0. All right, and let's talk about our last example set here, and that'll be density problems. Nope, just kidding. Density problems come at the very end. Let's talk about molar mass. So molar mass is how we convert from grams of something to moles of something, because we measure in grams in the lab, but we want to compare amounts in moles instead. And this is something that'll come into play a lot later in the semester, or it might even be next semester. So these are very important for chemistry. So we're going to convert 25 grams of water to moles of water. So this is a dimensional analysis problem. So our wanted is mole H2O we are given 25 gram H2O. Why is it so hard to draw a 2? So our data is going to be, we need to do our molar mass. So to do molar mass, we're going to look on the periodic table. And I know you guys can't really see this, but we're going to look at these numbers with the decimals on them. So I'm going to look at hydrogen right here, and I'm going to look at oxygen right here. So H2O is 2 hydrogens, so 2 times molar mass of hydrogen, which is 1.008 grams, plus the mass of 1 oxygen, which is 15.999 grams. And that's going to be and this is exactly how I'm putting this in my calculator with the parentheses and everything. So my molar mass of water is 18.015 grams of H2O is equal to 1 mole of H2O. So now let's do our conversion. So I start off with 25 gram H2O. Grams of H2O are on top, so it's going to go to bottom. So for every 18.015 gram H2O, I have 1 mole H2O. So 25, and then we have grams of H2O cancel, and we're left with just moles of H2O. So 25 times 1 divided by 18.015 gives me this unrounded number here, 1.38773. And I'm going to round to 2 significant figures, so that becomes 1.4 mole H2O. Okay, so that's our first one. All right, let's do our next one. Let's switch back to green. So it says, if you have 34.5 grams of NaCl, or sodium chloride, which is table salt, how many moles of NaCl do you have? So my data is going to be the molar mass of sodium, which is right here, plus the molar mass of chlorine, which is right here. I keep forgetting where my webcam is. So when I add those together, I have 22.99 grams plus, which is the molar mass of sodium, plus the molar mass of chlorine, which is 35.45 grams of chlorine. 22.99 plus 35.45. 58.44 grams of NaCl is equal to 1 mole NaCl. Okay, so now let's solve this one. This is my given, 35.4 grams of NaCl. Grams of NaCl on top, so grams is going to go on bottom. 54.44 grams of NaCl is to 1 mole of NaCl. Grams are going to cancel. 35.4 times 1 divided by 58.44 gives me this number here, 0.60575. I want to round to 3 significant figures, so that's going to become 0.606 mole of NaCl. All right, this one we're going to convert atoms of silicon to moles of silicon. So wanted we do, all right, it says convert 4.88 times 10 to the 24. My handwriting is getting a lot worse. Okay, that's sort of atoms of silicon, and we want moles of silicon. So our data, we're going to use Avogadro's number, so 6.02 times 10 to the 23rd. Jeez Louise. Atoms of silicon equals 1 mole of silicon. And I'm going to run out of room, so I'm going to have to erase all this and actually solve. Or I can actually just do it. Here we go. I'm going to cheat a little bit here. So I'm going to convert now. There we go. So that's my given. So atoms of silicon's on top, so we're going to do atoms of silicon on bottom. And when you put this in the calculator, I recommend you do this part in parentheses divided by this part in parentheses. So that's exactly what I'm going to do. 4.88 times 10 to the 24 divided by 6.02 times 10 to the 23rd. All right, and then my answer, which I'm going to write down here, I get 8.1063. This is 3 significant figures here, so I'm going to round to 3 significant figures, so 8.11 moles of Si. And I think I have one more example, but that could have been my last one. Let me check really quick. I do, okay. And this last one, it wants to know how many moles are represented by 118 grams of cobalt. So wanted is moles cobalt. Given is 118 grams cobalt. For our data, because we're just looking at cobalt by itself, on the periodic table, it is right here. And if you look right there, it says that for every 58.933 grams of cobalt, I'm going to have 1 mole of cobalt. So let's go ahead and solve now. So grams on top, grams is going to go on bottom. Grams cancels. 118 divided by 58.933. So I get 2.00227. I'm going to round that to 3 significant figures. Well, that means it's going to be 2.00 moles CO. All right, so now we're going to go through our density problems. Just kidding. Here we go. All right, so density is equal to mass over volume. So what is the density of 180 grams of methanol whose volume is 600 cubic centimeters? So density equals mass over volume. So my mass is 180 grams over my volume of 600 cubic centimeters. So 180 divided by 600 gives me 0.3 grams per cubic centimeter. And if I'm going to do significant figures here, I have 2 here, 1 here, and I already have 1 in my answer, so that works out really well. All right, so let's do our next problem. It says a block has a mass of 10.7 0.75 grams and a density of 7.8 grams per cubic centimeters. What's the block's volume? So one really cool thing about density is they have what they call a density triangle. So density triangle. So the density is mass over volume. So whatever one you're solving for, so if I'm solving for density, I have mass over volume. I'm putting my finger here like you can see me pointing. I have mass over volume. So in this case, I'm solving for volume, so I'm going to have mass divided by density. So volume equals mass over density. So 10.75 grams over 7.8 grams per cubic centimeter. Looks like a 5. There we go. All right, so 10.75 divided by 7.8 gives me this very long number, but I'm going to round to 2 significant figures because that's 2 and this one's 4, so I want 2 significant figures. I'm going to round to 1.4 gram. Oh, no, not grams. Grams is going to cancel. It's a volume, so your grams cancel here, so I'm just left with 1.4 cubic centimeters. All right, and then I think we have one more left, and that'll be all the examples for this unit. Okay, it says Jeff has a density of 1,015 grams per milliliters and a volume of 27.3 milliliters. What is Jeff's mass? So if I'm solving for mass, I'm going to do density times volume. So that means I'm going to do 1,015 grams per milliliters times 27.3 milliliters. I have 4 significant figures here, 3 here, so I want 3 in my answer. 3. I want 3 significant figures in my answer. So my unrounded number is this. So in 3 significant figures, it's going to be 27700 grams. All right, there you go. If you have any questions about anything from this unit, please feel free to message me. I will be happy to help you out. Hopefully this helped out. Watch the other videos. That's another chemistry teacher I found on YouTube. He is really great and has gone through things really well. So let me know if you have any questions, and good luck.